Well, welcome back to our discussion about solving trigonometric equations. And in this video, we will be talking about how to solve trig equations that are quadratic in form. But before we jump into that, we're going to introduce a new concept. In the past two videos, we've been talking about solving for general solutions or all possible solutions. We're going to introduce this concept here where we talk about solving for the principal solutions only. And all that means is we are wanting to identify the solutions that are found on one rotation of the unit circle. So everything from 0 to 2 pi, but nothing beyond that. Okay, so nothing negative and nothing greater than 2 pi. With these types of examples, we will be seeing equations that are quadratic in form. Okay, so if you have an equation that's quadratic in form, you are just going to treat it like a quadratic equation. And the way I'm going to show you how to do that is first set the equation equal to 0, and then we're going to sub out the trig function so that we can look at it more objectively like a true quadratic. And then we'll factor it and set each factor and then set each factor equal to 0 and solve for x. So let's walk through that process with this particular example. We have 2 cosine squared of x plus 3 cosine of x equals -1. Now we know this is quadratic in form because of two things. One, you have only one trig function within the equation. So all I see are cosines. I don't see sine, tangent, anything besides that, okay? The other thing is the highest degree is a squared, and I may or may not have a trig function that is not being squared. And I may or may not have a constant for that matter. The key thing is we're going to have no more than one trig function, and that trig function has at least one term that is raised to the second power. So first, let's set this equal to 0. So let's move that -1 to the left-hand side of the equation, and then we could say 2 cosine squared of x plus 3 cosine of x plus 1 is equal to 0. Now, we see that it's quadratic, but maybe it's harder to see it as a quadratic equation. So let's say that u is equal to cosine of x. Well, if u is equal to cosine of x, then 2 cosine squared of x would be the same as 2u squared. And 3 times cosine of x would be 3u. So I'm going to treat this like the equation 2u squared plus 3u plus 1 is equal to 0. Now, I'm going to go ahead and solve that quadratic, and you can use any method that works to solve this quadratic. I will rely on factoring because to me that is the fastest way. I know that this quadratic factors to 2u plus 1 times u plus 1 is equal to 0. Then I'll back substitute my original argument back in. So 2 cosine of x plus 1 times the cosine of x plus 1 is equal to 0. Now you can go ahead and solve for u and then back substitute. Either way is fine. So now I'm going to set each of those factors equal to 0 and solve. So 2 cosine of x plus 1 is equal to 0, and cosine of x plus 1 is equal to 0. Let's isolate the trig function. So we'll say the cosine of x is equal to -1/2 here and -1 here. And then pull the angles from the unit circle that have these cosines. Which angles have an x-coordinate of -1/2 and -1? Okay, there are 2 for the first one, so that will be at 2 pi over 3 and 4 pi over 3 on the left-hand side of the unit circle. And then where's a cosine -1? Which angle measures have an x value of -1? That will be at pi radians. Our solution set for this equation is pi, 2 pi over 3, and 4 pi over 3. Okay, here we have a couple of additional examples. We're going to do the same thing. We are looking for principal solutions, so we're only concerned about all the solutions on one rotation of the unit circle. So let's start with this first one. 2 sine squared of x is equal to negative sine of x plus 1. All right, and in this case, we're going to bring everything to the left-hand side. So that will be 2 sine squared of x plus sine of x minus 1 is equal to 0. And then I will write this as a quadratic without the trig function. I will let my substitution be u is equal to sine of x, and then substitute that in. So I'd have 2u squared plus u minus 1 is equal to 0. All right, and so when I factor that, I'll end up with 2u minus 1 and u plus 1 is equal to 0. And now I'll back substitute my trig function. So I'd have 2 sine of x minus 1 times sine of x plus 1 is equal to 0. Set each of those factors equal to 0 and isolate the trig function. So the sine of x is equal to 1/2 and the sine of x is equal to negative 1. And so I'll get 2 answers out of that first equation and 1 out of the second. Which angles on the unit circle have a y-coordinate of 1/2 and negative 1? That will be at pi over 6 and 5 pi over 6 for this first one, and 3 pi over 2 for the second one. All right, and so that will be my solution set. Pi over 6, 5 pi over 6, and 3 pi over 2. For the second example, we're going to work it through the same way. We see it's a quadratic, one trig function. The maximum degree is a squared. So we can set the whole equation equal to 0. So we would say 2 sine squared of x minus 4 sine of x minus 6 is equal to 0. We will let our substitution be u is equal to sine of x. And we'll treat this like 2u squared minus 4u minus 6 is equal to 0. Well, right away you can factor out a 2, and then you would have u squared minus 2u minus 3 is equal to 0, which will factor to 2u plus 1, u minus 3 is equal to 0. Okay, so now back substitute, and we can say that we end up with 2 times sine of x plus 1 and sine of x minus 3. And that is all equal to 0. We're going to set those factors equal to 0. We don't need to worry about the 2 because we can just divide that out. And we would end up with the sine of x is equal to negative 1 and the sine of x is equal to 3. Now this is a little bit interesting, okay? Because we definitely know that the sine of x is equal to negative 1 at 3 pi over 2. But where is the sine of x equal to 3? And that's tricky because of y equals sine of x. You'll remember that the range of that graph only goes between negative 1 and 1. And so there is no solution from this factor. Okay, and that is because there's nothing that will satisfy this equation. So the only solution to this trig equation will be 3 pi over 2. A couple more examples for us to walk through. And look, these look a little simpler. Okay, and in some ways they are. Notice that they're still quadratic in form, but there's no middle term. Okay, so let's take a look. This first example, 4 cosine squared of x is equal to 1. We will set that equal to 0 and subtract 1 on both sides. We'll say that that is 4 cosine squared of x minus 1 is equal to 0. And we will sub out the trig function and we'll say that that is u is equal to cosine of x, and we would have 4u squared minus 1 is equal to 0. We know that this factors by 2u plus 1 and 2u minus 1 is equal to 0. And we will back substitute our trig function. So we would end up with 2 factors of 2 cosine of x minus 1 and 2 cosine of x plus 1 is equal to 0. Now, if I set both of those factors equal to 0 and isolate the trig function, we will end up with cosine of x is equal to 1/2 and cosine of x is equal to negative 1/2. And so we will end up with 4 solutions here, 2 from the left and 2 from the right. The angles on the unit circle that have an x coordinate of 1/2 are pi over 3 and 5 pi over 3. And the angles on the unit circle that have an x value of negative 1/2 are 2 pi over 3 and 4 pi over 3. So my solution set, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Very, very similar problem, this next one. We're going to, but we're going to have a little bit of creative factoring here, and you'll see how that works. Let's set this equal to 0 by subtracting the 3 to both sides, and then what do you think our substitution will be? If you said u is equal to the tangent of x, you'd be right. And so we can rewrite this as 9u squared minus 3 is equal to 0. Now I can factor out a common factor of 3, and then I would have 3u squared minus 1. Now that's technically not a difference of squares, but we are going to treat it that way, okay? We're going to treat it that way because we can take the square root of 3u squared and get the square root of 3u as our first term and plus or minus 1 as our second term in our factoring. That's really very nice because we do know that tangent has the square root of 3 in it often. So let's go ahead and back substitute our trig function. We will replace our u's with tangent of x and set our factors equal to 0. Now let's isolate our tangent of x, okay? So getting our tangent of x isolated, we would get tangent of x is equal to negative 1 over the square root of 3 and positive 1 over the square root of 3. And if we rationalize those, we would have plus or minus the square root of 3 over 3. We know that the angles that have a tangent of plus or minus the square root of 3, and we know that this happens at our 30-degree angles, which are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So we can say that those angles will comprise our solution set. All right, the next one is similar to what we've done before, except we have secant. And so we're going to use a reciprocal a little bit later. Let's go ahead and do what we've done before by setting this equation equal to 0 and substituting out the trig function. So u will be secant squared. So if we say that u is secant squared, then we would have 4u squared minus 2. And then we would think of that as factoring out a 2, and we would have 2u squared minus 1. We're going to factor that like we did over here. And we're going to say that this will factor as 2 times the square root of 2u plus 1 times the square root of 2u minus 1, and that's all equal to 0. Back substitute our secant in there and set those equations equal to 0, and now solve for secant. Isolate our trig function. So in the left-hand equation, we'll have secant of x is equal to negative 1 over the square root of 2, and our right-hand equation will give us the secant of x is equal to positive 1 over the square root of 2. We don't really know secant of x all that well, but we do know it's reciprocal, so let's reciprocate both sides of both equations. That will give us the cosine of x is equal to the negative square root of 2, and the cosine of x is equal to the positive square root of 2. Okay, so where does that happen? Where is cosine plus or minus the square root of 2? And that's another one that is greater than 1 and less than negative 1. So it falls out of the range of y equals the cosine of x. So we are going to go ahead and say that this equation has no solution. All right, that wraps up quadratic form trig equations, and I will see you next time.